So this is a course on mathematical structures. It is a course offered under NITheCS, National Institute of Theoretical and Computational Sciences. And we now have the first lecture of the course. The course will be presented by various mathematicians working in the mathematical structures program at NITheCS. And the idea of the course is to introduce basic mathematical structures in the sense that will become apparent in a moment, and to also discuss possible links, existing links between structures that are of fundamental importance for mathematics. So we will be looking at mathematical structures that are important throughout mathematics, and not just in mathematics, also in applications of mathematics. But what we mean by a mathematical structure is something a bit more specific than what you might think. So let's first talk about that. In a very broad sense, one might think that mathematical structure means any kind of mathematical entity. In some sense it does, but in some other sense it doesn't. There is a way to formalize mathematics based on axioms called set theory. And what we mean by mathematical structures are mathematical entities that have been formalized in that language of set theory. And then usually mathematical structures take the form of some set X equipped with some additional data, which also are sets, which relate to the set X in a certain way. Now, this is not a formal definition of mathematical structure. In fact, we are not going to go after formal definition. We are more trying to kind of put together an intuitive notion that applies to specific examples that we're going to look at. But it doesn't mean that people haven't tried to formalize the definition of mathematical structure. They have. And that's a separate topic which we are not going to go into. So let's look at some examples of what we mean at the intuitive level, what we mean by a set equipped with some additional data. Well, this could be a set equipped with no additional data. In that case, our mathematical structure is just a set. You probably have the same intuition for what a set is as I do. You can think of it as a bag of abstract entities. They could be abstract entities, or they could be concrete entities, which we usually represent as dots. And in a set, what matters is the contents of the set, these things called elements, and not how they are arranged among each other. What shape they take, that's completely irrelevant. Next example of a mathematical structure is a set equipped with a binary operation. So what is a binary operation in a set? Well, in a primitive language, a binary operation takes as an input a pair of elements of the set, and as an output, it produces some other element of the set. We can, for example, write it like this. This doesn't have to be the usual multiplication of numbers. This could be an abstract way of combining two elements into a third element. In a bit more advanced language, what we mean here is just a function from the Cartesian product of x with itself to x. So we might write a dot for this function, and the usual functional notation of evaluating a function at a variable is reconciled with our notation by saying that this expression dot of xy will be written as x dot y. So they mean the same thing. Because we don't put any restrictions on the binary operation, it can be really arbitrary binary operation. You might find it surprising that such a structure actually has a name, even though it's a very general type of structure. It's called a magma. And the reason why it's called magma is because magma is also a very formless thing. So these magmas are going to be the topic of our first lecture on mathematical structures. So we're going to now stop here discussing the general idea of mathematical structure, and we're going to start discussing magmas. Well, firstly, let us try to give some examples of magmas. But perhaps even before we give examples of magmas, maybe we want to first give a bit more precise and elegant definition of what a magma is. So before we already said that a magma is a set X equipped with a binary operation, but what do we really mean by the word equipped? As I said earlier, we would like to think of everything as it can be formalized in set theory. And so then the question becomes, how do we formalize the idea of something equipped with something else? And this is done as follows. So a magma is an ordered pair M dot, where M is a set and dot is a binary operation on M, by which we simply mean that it's a function from M cross M to M. And once we state this definition, then after the definition, we can introduce notations such as writing the value of dot at the ordered pair xy of elements of x, writing it as x dot y. Okay. Are there any questions on my formalization of the definition of a magma? Do you want to ask anything for clarification regarding this definition? If you do, please go ahead and do that. You can ask in the chat, or you can ask by turning your microphone on.
Prof, does this use of a dot in any way have any sort of correlation with the dot product or inner product, or is dot a placeholder for a binary operation?
No correlation. It is a placeholder for a binary operation that could be any operation.
Okay.
Inner product wouldn't even qualify as an operation in our sense, in the sense we define here, because with inner product you're taking two vectors and the result is a real number, right? If you've got vectors over a real number field. Here we are interested in operations being from m cross m to m. The same values must be of the same type as the input into the operation.
Thank you.
So let us then indeed list some examples. The set of natural numbers and usual multiplication of natural numbers. Now, I could go on making a list of very natural examples of this notion with, let's say, addition and so on, right? But let's try to come up on the spot with some unnatural examples. Still, let's say with a set of natural numbers, and let's call this operation star, and let's define n star m. And now I would like you to suggest for me, please, what we could put here to form this operation to be of the kind we haven't seen before. The purpose of this exercise is to demonstrate that really our operation can be anything we like it to be.
Could you just maybe write a new letter, which is the element of natural numbers?
No, I want to be specific. I want to give a specific definition of how n star m is worked out. I want to have a specific value there. But this specific value should of course be designed out of n and m. So basically asking for a possible way of creating a new number out of two given numbers and then declaring that to be our operation.
Into the power of m?
I said something that's not familiar to us.
Okay. I thought you meant like familiar that we've already discussed. But just checking the output of this would need to still definitely be in the natural number sequence in our natural numbers, so it couldn't be something like subtraction, right? Or at least if it was subtraction.
That's a good point. Yes, that as we said here, we want the operation to have its values inside the same set. Yeah. So subtraction wouldn't work. There are so many possibilities here that maybe that's why it's difficult to choose. But because there are so many possibilities, I really would like you to give me some of them.
Could the answer be just n star m equals to, is it possible for it to be just natural numbers equals to natural numbers, like the whole set?
No, but or this.
Yes.
No, that's not possible because n is not an element of itself, right? We said here that this needs to be, this star needs to be an operation that goes from m cross m to m. So in our case, m is n, right? So it needs to be a function from n cross n to n. So if I have two numbers n and m, it must give me another number. Now you're saying that it must give me the whole set of numbers. That wouldn't work because this is not a number. It needs to be an element. Whatever goes here needs to be an element of the set of natural numbers.
Can it be a composition of things we're familiar with? So could it be m to the m factorial?
N to the power m factorial. Is that your suggestion?
Yes.
Okay. So does anyone think that this would not make it work? Let's check if this can work. We said that the star thing should be a function. So once n and m is given, there must be a unique value for n star m. Is this expression uniquely determined once we know what n and m are? Well, as far as I'm concerned, the answer is yes. And then the other thing we want to check is whether this thing is actually a natural number, and indeed it is. When n and m are natural numbers, n to the power m factorial is also a natural number. So this seems to be a good example of a magma. And of course, one can go on like this, introduce various different kinds of magmas, where, for instance, in this example, we could have 2 times n plus n times m plus m squared. Why not? Right? And so on. Okay. So now that we have looked at the definition of a magma and looked at some examples of magmas, let us explore what kind of things we can do with a magma. And in particular, let's explore what kind of features of elements of a magma are interesting to consider. So I'm going to make a list of a few definitions now, all of them in the context of a magma, and then we can try to interpret what these concepts amount to in the 3 examples we mentioned. In a magma, an identity element, I, let's call it I, it's not the complex number I necessarily. An identity element I is an element. And in fact, let me be a bit more precise in my language here. So let's fix notation for a magma. So in a magma, M with operation being dot, an identity element I is an element of M such that I times X equals X and equals X times I for every X in M.
Prof, when you said times there, do you mean if you perform the operation? So
Yeah.
If we go back to my
I call it times
okay.
just because we've been writing it as if it was a multiplication, but it's just a language I use, but I don't really mean multiplication in the usual sense. Okay, so let's go back to our examples and let's see if we can find identity elements there. In this first example, where our operation is actual multiplication, which element, if any, is an identity element?
Is it 1?
Yes, that's right. It's 1. So let's make a note here. I equals 1 is an identity element. Now let's look at the second example. In this example, which element is an identity element, if any?
Does the identity element return can you stipulate as to which position it can go in? So like right now, so in this example, I believe that 1 would be an identity element as long as it's in n's place. But if it's in m's place, then not necessarily. Oh, well, actually, there is one for different variables, I guess.
Well, look at this. We're forcing I times x to equal x, and also x times I to equal x as well. Right?
Yeah. So okay, yeah. So actually, I spoke quicker than I thought. Would it be 1 in no matter which position? I suppose.
Well, let's try. Let's see. So if n is 1, let's say, right, and I take star of 1 with m, I'm going to get 1 to the power m factorial. And according to the definition of the identity element, that must equal m, but it's not. So 1 is not an identity element. Maybe there is another one. Maybe some other element is an identity element. We could try to write down what it means to be an identity element in the specific case and maybe go from there, investigate from there. So if there was an identity element I, that thing starred with any m must equal I to the power m factorial. Okay. Now, on the other hand, because of the other equality, because of this equality, also n starred with I must equal, sorry, I said nonsense previous time. So I star m must equal m, right? So what I wanted to say rather is that this thing, which is equal to I star m, must eventually equal m. So I should be such that this expression equals m for every m. At the same time, I should be such that so what is n star I? N star I is n to the power I factorial, right? That should equal n. Now, and that should happen for every n, right? For every n, this should equal that. Does our set of natural numbers include 0? Well, I usually include 0 among natural numbers, so let's make this remark here that n is the set of numbers 0, 1, and onwards. That does simplify things a little bit, because now if I put 0 here, I'll get 0 to the power I factorial, which is always equal to 1, irrespective of, sorry, what am I talking about? So it's equal to, it's not equal to 1, of course. It would be equal to 1 if I factorial was 0, but that is never 0. So it actually equals 0. So the 0 case is fine. For a moment I thought that the 0 case would help us, but it doesn't. For the 0 case is fine. What if we try and put n equals 1 here? Remember, this should hold for every n, right? Then we'll get 1 to the power I factorial, which is always 1. So for n equals 0 and 1, this will be true irrespective of what I factorial is, right? So it doesn't really put any restrictions on I factorial. What if we put 2 in the place of n? So then we'll have 2 to the power I factorial equals 2, right? Now this forces I factorial to be 1, I believe, yes? There are 2 cases where I factorial is 1. When I is 0 or when I is 1, right? In all the other cases, it's not. No? And now we take this thing and put it back into the other equation. So if there is an identity element for this operation, it must be either 0 or 1. But now we take it back and put it here, and we then see that neither of them work, right? If I was 1, we will have 1 to the power n factorial, and that equals 1. But that wouldn't equal m for every m, right? So maybe this time around I wanted to write it the other way around. So this equals 1, and that never equals m, except when m is 1. But we want this to be for every m, so that is a failure. And then the other case is when we have I to be 0, and 0 to the power n factorial is 0. And that also can't be equal to m for every m. So this little investigation here convinces us that there is no identity element for this magma. Would anyone like to ask any questions?
Yeah, I'd like to ask a question.
Please, go ahead.
So like, is it possible, like, okay, like for example, if you have 2 to the power 2 factorial, is the like, it's going to be like, it's still going to give you like, okay, let me say 2 times 2, we know that 2 times 2 is 4, then 2 to the power 2 factorial is still 4. Does that mean that it's an identity element?
No, remember we wanted here to have that equal to 2, not to 2 times 2. It needed to be equal to 2.
Is there a word for these, call it fake identity elements, that look like they'll work because they work with in place of the one but not the other?
I don't think I understood the question.
Is there a word for these elements that look like they could be identity elements because they work in the one direction but not the other? meaning they work in place of
Yes.
n, or they work in
There
place
is-
of m, but
there-
not the other.
There is terminology for left identity and right identity element.
Okay.
What about the last example? What about this third example here? Does this have an identity element? I would like to leave this as a little exercise. So is there an identity element in this third example of a magma?
I would think not, because no matter what you do with n, you'll always be left with m squared.
That's a nice intuition. It will be nice if you can fulfill that intuition into a proof, like the one we produced here for the second example, that identity element does not exist. Now, okay, so we saw that sometimes it exists and sometimes doesn't, but then when it does exist, we might wonder whether there is only one or whether there are more than one identity elements. And if we go back to the natural numbers with multiplication, I think you will agree with me that certainly there is only one identity element. There's no other number that has the feature that multiplying with anything else gives us back that thing, right? But what about in general? And in fact, this will be our first theorem about general magmas, where we're going to claim that in every magma, there is at most one identity element. How do we prove that?
Should we use proof by contradiction and assume
Okay, so let's say that there are two. We don't necessarily need to assume they're different from each other. We can allow them to be the same or not. We'll figure out if they're the same or not. So that there'll be two of them. So let these both be identity elements. And now we want to show that they're the same. So let's see what happens if you multiply them, right? I times I prime. What is this equal to?
I think it's equals to I.
It equals to I because I prime is an identity element, right?
But it also should be the r prime, because r prime's an identity element.
Because I is an identity element, you mean?
Yeah.
True. So that's how we get that the two need to be equal. So you see, you can't have more than one. If there are two of them, they will always be the same. Okay, now there's something interesting we can do about a magma. We can take a magma M and map it into another magma. Well, at least try to map it into another magma, which has a very interesting structure. So I'm going to call it AND M. This notation here stands for end of functions. Of M. In other words, they are functions from M to M. Okay. Why is this thing a magma itself? Because we can compose functions. We can take two functions and compose them, and that's how we get a binary operation. So the way we are going to map M in there, in other words, build a function from M to NM, is the following. So every element of M, let's call that element X, as we have been doing before, will map to the following function from M to M. This function will be called X dot blank. What this function does, it maps Y to X dot Y. If we go back to our notation for multiplication, if we go back here, right, we can think of this as a function of two variables, right, the variable X and the variable Y. But as soon as I fix one of the variables, as soon as I fix X, for example, then I can think of this as a function of one variable, of the second variable. This is exactly what I'm doing here. I'm fixing one variable, and then I'm thinking of this function, the X dot Y thing. I'm thinking of it as a function of Y, where Y is mapped to X dot Y. So every element of the magma gives rise to a function from M to M. Maybe an illustration of this process will be useful. So let's consider the example where our magma is the magma of natural numbers, and let's see what function it will give rise to. In fact, I would like to take not the one with multiplication, but I would like to take the one with addition. So natural numbers with addition instead of multiplication. So now I'll be mapping a natural number. Maybe I should call this thing n. For each number n, I'll be creating a function from n to n, and this function will map m to n plus m. So what am I basically doing here? I'm shifting all the numbers through this function. I'm shifting all the numbers by n, right? I'm adding to everything. I'm adding n. So I'm shifting everything by n. So it's a kind of translation mapping. So that's one of the fascinating things about a magma is that every element, right, can also be seen as a function. Okay. Now going back to the abstract scenario of having some magma here, which allows us to see every element as a function, we might wonder about what does composition do? In other words, what does composition of functions, so a binary operation on this side, what does it do to how the elements in the magma are behaved? Okay, so what do I mean by that? Let's consider, well, first of all, let's maybe have a name which for this function that will be easier to remember. Let's call this function r with subscript x. So Rx of y is x times y. Now, what happens if I take, maybe I want to insert some space here. What happens if I take Rx and I compose that with Ry, right? And then I evaluate that result on some variable z. So once I think of elements of my magma as functions, now I can compose the functions and see what happens, right? Okay, so by definition of composition of functions, this is the same as applying Rx to Ry of z, isn't it? Well, what is Ry of z? Ry of z, as we agreed, will be y times z. And Rx of that will be x times y times z. How will this differ from having considered the function r indexed by x dot y? So I've got my x and y, I interpret them as functions, right? And then I compose these functions. Now I want to, before interpreting something as a function, I first want to multiply them inside the magma, and then interpret it as a function, and then evaluate it at variable z. Let's see what the result will be. By definition of r, this will be x dot y dot z. And looking at these two expressions, we are reminded of some rule that we learned at school even. What is that rule?
Association.
Right, associativity. At least that's how I call it. We know that for many operations that we encounter in mathematics, we have this law of associativity, which says that these two expressions have the same value. So in other words, this always equals that. In our context, associativity would then amount to basically prove the theorem now, which says that in a magma, the operation is associative if and only if Rx composed with Ry always equals Rx dot y. Why always? Because for every z, we're requiring this to be the same as this for every z, right? And as well as for every x and y. So we will then be getting that this is always the same as that. So that holds for all x and y in the magma. So we have a new interpretation of the rule of associativity. And in this new interpretation, I want to highlight this thing here. In this new interpretation, associativity rule becomes a rule of compatibility of multiplication of elements and composition of functions. So basically, the associativity rule tells us that when we think of elements as functions, and then we compose them as we know how to compose functions, this is the same process as first multiplying those elements by the operation of the magma and then thinking of that as a function. So composition of functions is compatible with multiplication of elements in the magma. So we kind of are saying that this magma is well behaved from this standpoint, from this philosophy of viewing its elements as functions. Magmas in which the operation is associative are very important in mathematics, and there is a special name for such magmas. They're called semigroups. Semigroup is a magma where the operation dot is associative. So in this new language, our theorem states that a magma is a semigroup if and only if multiplication of elements is compatible with composition of those elements seen as functions. If on top of this, we even have an identity element, then there is yet another name. A semigroup having an identity element is called a monoid. And what I would want to do now is to highlight all the mathematical structures that we've introduced here. Semigroups are mathematical structures, monoids are mathematical structures, and magmas are mathematical structures. Okay, that one was already highlighted. Let me make it the same color as the other two.
Sorry, Prof, what is a semigroup?
A semigroup is a magma where the operation is associative.
Sorry, I don't know why I was reading is as if. That's my own.
Okay. We can go back to these examples and see which of them were semigroups and which of them were maybe on top of them were monoids. Is this a semigroup? And with multiplication? Multiplication of numbers is associative, right? In fact, it's a
Yes.
monoid because there is an identity element. So this thing is a monoid. This one here, the star operation, that one we saw it doesn't have identity elements, so it can't be a monoid. But is it a semigroup? For it to be a semigroup, we will have to have star operation to be associative. Let's write down what it means for star to be associative in this case, and let's see if it is associative or not. My intuition tells me it's probably not associative. It's probably highly non-associative, but let's confirm this. So to check for associativity, we'll have to form two expressions, n star m star k, and compare that with n star m star k. So let's look at the first one first. We evaluate the terms as they appear in brackets, right? In the usual way we compute expressions like this already from school. So what is n star m? That's n to the power m factorial. And now we have to take a star of this with k. So that will be n to the power m factorial to the power k factorial, right? What about the other one? The other one is n star m star k is m to the power k factorial, right? And this one will be n to the power m to the power, sorry, yeah, m to the power k factorial. And I think by the appearance of these expressions, I think we're all quite convinced that they will hardly ever be equal to each other. And if we want to double check that, we could just put in some specific numbers and see that they're really not equal to each other. Remember, these have to be equal for all n and m and k in order for this thing to be associative. They're not equal. So we can say then that this thing here, the second example we were considering, is not even a semigroup. It's a genuine magma in the sense that it's a magma, but it's nothing more than a magma, at least in terms of the properties we considered so far.
Prof.
Yes.
Isn't it supposed to be n to the power m to the power k factorial all factorial?
Yes, it is. Thank you. Yeah, I made a mistake there. It is supposed to be that. Thank you very much. But that doesn't change the outcome of it's still different from the other expression, right? Okay. What about the last one? We already conjectured. I mean, we already said maybe there is no identity element, but is this operation associative? And probably we feel that it's not, but let's leave it as an exercise as well. Okay. All right. Any questions so far?
Prof, could you prove that it's not associative just by showing it's not commutative? So, like for the
No.
example I gave with into the m factorial, it's not even commutative. So then, could you not, instead of having to do the proof with k, could you not just prove it since not even n and m are commutative
No,
then
no, you
it
can't.
can't be
You can have
associative.
operations that are not commutative, but that are associative. And actually,
okay. I
that's
didn't know
a good.
that. I didn't think that was.
So that let me show you
that was
that.
possible.
That's
Okay.
an important example. A very important monoid, in fact. But first, we will treat this as a magma, and then we'll get convinced that it's actually a monoid. Is the following: let M be the set of all words, and I'm going to put this in quotation marks, in an alphabet. So this is an example that's very important in computer science, but also in mathematics for different reasons. Well, maybe not very different reasons, but so let M be the set of all words in an alphabet A. What does that mean? It means sequences A1, A2, A3, up to some AN, where the length of the sequence is not fixed, where these terms of the sequence are just elements of A. So for instance, if our alphabet consists of usual letters A, B, C, D, E, and so on, up to Z, right? Then what will be the elements of M? Well, I said here sequences, and I didn't exclude the possibility of n being 0, which means that sequence is empty. So that there is no, there are not, basically that means that there's no sequence. So we allow empty sequence as well. We can allow empty sequence as well. So that will be empty word. That's basically when you don't write down anything, right? It corresponds to the action of not writing anything down. And then individual letters will be words, just sequences having just one term in it. But then also combinations of those. Let's say AB will be there, right? Then at some point, able will be there, and so on. So we will really can think of these as words. Words are basically sequences where the terms of the sequence are letters.
Prof, if this includes not writing anything, can't it then be the set of, or couldn't it then be all sentences, not just words?
Sentences. So in a sentence, we need a empty space, but it still occupies it still occupies some space, right? The empty space. So
Oh,
then
okay. Okay. Yeah. So this
we
is
must
just
then include, if we
okay,
want that
yeah.
as well, we just must include it
So
as an element
that's
of
white
the
space, not empty space.
Yeah.
So that first element isn't white space; it's empty space. Okay.
Yeah, yeah. But if we want that, then we can include in A that character, the white space
Okay.
character, and the punctuation and everything. Okay, but now we just describe a set. We want to turn this into a magma. So I want to describe how we multiply two sequences or two words. So if I call my sequence, okay, let's just stick with this notation. So define one sequence times another, let's say B1 up to BM, to be just forming a longer sequence. So what is called concatenation of words, when you just put these sequences next to each other and you get a longer sequence. Okay. This is called concatenation, and I hope my spelling there is correct, of words. And I keep calling these words, I keep putting it in quotation marks, but in fact, in mathematics, the term word is an accepted term for a sequence like that. So here is a little theorem that the set of all words even in a given alphabet equipped with the operation of concatenation is not just a magma. It clearly is a magma, right? Because the output of my operation is still a word, but it's actually a semigroup, and not only a semigroup, it's actually a monoid. We will only give a sketch of this proof of this theorem. So to get convinced that it's a monoid, we need to get convinced it's associative, and that there is an identity element, right? So associativity is, I think, quite obvious, right? So imagine you've got one word, you multiply that with another one, and then you further multiply with a third word. So when you first perform operation inside the brackets there, you will get this longer word. And then when you perform operation here, and I've been kind of missing the dots there, I should keep the dot there, it becomes an even longer word, right? But now that longer word could have been also rearranged in a different way. We could have designed it by first having operated on that side and then with that. So we could think of this as the word AN multiplied by the word B1 to BM C1 to CK, and then further decomposing this as a product of the B word and the C word. And then that's it. That's our associativity, right? So you see the brackets have now been rearranged. What about the identity element? So we need an element I such that when I take that word I and I concatenate it with another word, right, I'll get back that other word. And it doesn't matter on which side I do this. What do you think will be the identity element? Any ideas?
The empty space element?
Yep. It's given by the empty word. So the empty sequence, in other words. I haven't told you what do I mean by empty sequence in a formal mathematical language, but neither have I told you what I mean by sequence in a formal mathematical language. Maybe that's worth of a remark. A sequence an up to an, a1 up to an of elements of a set A is defined as a function. We often call this function A from the set of numbers from 1 to n to the set A, where the value of the function at I is given by the ith term of the sequence. Now, when n equals 0, right, we have that the set of numbers from 1 to n equals empty set by convention. I mean, after all, we're listing all the numbers from 1 increasingly going up to 0, but we can never go up to 0 increasingly, so there's nothing to list. So that is empty set by convention, which then results in a unique function, because there's exactly one function from the empty set to every other set. If I see a function as a set of ordered pairs, then of x and corresponding y values, then this exactly one function is this unique function that exists. There will be the empty set of ordered pairs. So it results in a unique function, and when we refer, okay, let me first say that this function is called the empty sequence, called the empty sequence, and then I think it will be obvious that by empty word we actually mean the empty sequence. Okay, so we have now another example of a monoid. This monoid is not commutative. So what does it mean that it's not commutative? Maybe we should first formally introduce what it means for an operation to be commutative. A commutative magma you know what? I don't want to call this a commutative magma because later on I might define commutativity slightly differently. So I'm going to say the following: a monoid m.1 is said to be commutative when x dot y equals y dot x for every x and y in M. And I think it should be fairly obvious that the monoid of words is not going to be commutative. Because if you rearrange letters in your word, you will get a different word, right?
And Prof, can only monoids be commutative?
So I do want to define commutativity in a slightly different way than this when we leave the context of monoids. That's why I state it like this. But otherwise, people do consider exactly the same axiom also for magmas. But I will use a different axiom for magmas for commutativity and deduce this as a consequence in the case of a monoid. So for pedagogical reasons, I didn't state this definition in a more general context. But otherwise,
Okay.
yeah, one can also consider the same axiom on just any magma. So let's maybe make a remark here that the monoid of words is you know what? I'm going to turn this remark into a theorem, actually. Let M with dot be the monoid of words in an alphabet A. This monoid is commutative if and only if there are some cases when the monoid of words is commutative, and I would like you to tell me which these cases are. So let's first explain why did we say that the monoid of words is not commutative. Like, for example, if you have C, the musical sound. C, the word C is not the same as the word is, right? If concatenation was commutative, then it wouldn't matter whether we place first S and then I or the other way around, right? So that's why we say that the monoid of words in general isn't commutative. But now, can you think of a situation? And so already in this example, A is an alphabet that contains as letters S and I. Now, can you think of an example of an alphabet where you choose alphabet in such a way that it actually doesn't matter in which order you put things, that concatenation does become commutative?
An alphabet with the same word?
Is it not when you concatenate it with the empty word?
Commutativity is a universal property. It must be true for all x, y. But what you're saying, for that does make sense. We could take the alphabet itself to be empty, right? No letters. If there are no letters to use to form words, then we will have only one word. That will be the empty word. And of course, empty word concatenated with the empty word, their order can be rearranged because on both sides we have the same word. So that's one case, when A is the empty alphabet, when A is the empty set. Which other case is there, or are there, for an alphabet?
When our alphabet only has one letter.
Wonderful. That's great. Well done, chat. Exactly. When there is only one letter, look what happens when there's only one letter. So if there's only one letter, then the only words we can write, let's say, is this. And now I write that word and concatenate it with that one, right? That is the same as this concatenated with this, because all what matters in the end is the amount of letters. Since all the letters are the same, then the words are distinguishable by their length. And of course, the length will be the same irrespective of how I arrange them. Huh? So the theorem states that this will be a monoid of words, will be commutative if and only if either A is equal to the empty set, or A has exactly one element. I would now like us to look at this example in more detail. The example when A has exactly one element. Consider A to have exactly one element, and let me call that element a stick. Okay? Then what are elements of the corresponding monoid of words? We have the empty word. We have the letter stick, right? We have a word where we concatenate stick with itself. 2 sticks, 3 sticks, 4 sticks, 5 sticks, and so on. Does this resemble anything we know? If I have
What was that tally thing we learned in like primary school where you do a tally of counting?
Yeah, if I have a word of length n in this monoid, right, and a word of length m, and if I multiply that, right, I put all these sticks together, how many sticks will I get as a result?
N plus m.
Exactly. So
Prof, would the concatenation of the empty word with a certain number of sticks and the concatenation of a certain number of sticks with the empty word be one element or 2 different elements?
Concatenation of 2 things always results in one element that you create out of those 2.
Yeah, what I'm meaning is if you concatenate the empty word with 1 stick and then do the concatenation of one stick with the empty word, are they the same element or are they 2 different elements?
That's why the empty word is an identity element, because the empty word, when you concatenate something, remember the empty word doesn't occupy any space. So when you concatenate, you just are left with whatever you concatenate it with.
Okay.
So you see, we can think of the elements of this as numbers, 0, 1, 2, depending on how many sticks we have. And the operation of concatenation now turns into addition of numbers. So we could say that the monoid of words in an alphabet A having exactly one element is essentially the same as the monoid of natural numbers with addition as the operation. This is really fascinating because before a fine, refined number system was introduced, the way of writing numbers, right? A natural way of writing numbers would be just to write sticks next to each other, huh? And these are words, in the sense that you have symbols written next to each other. And so now you see how numbers and language come together. right? So our natural number system now is kind of part of our language in some sense. It emerges from the idea of writing things next to each other. It's very interesting. And what is more interesting is that this is the case when it's commutative, because we know that addition is commutative, of course. But as soon as you have more than one symbol that you use for forming words, then it's not commutative anymore. So we're kind of fortunate that with the one symbol thing turned out to be commutative, that we have commutative addition. Otherwise, life would be so difficult if adding natural numbers wasn't commutative, right? But there is something dodgy in this last statement I wrote. I said, is essentially the same as. And that doesn't seem like a mathematical notion. What do we mean by saying essentially the same as? We would like to give a precise definition of what it means for one magma to be essentially the same as the other one. We want to have, just like with all the other things in mathematics, we want to have a precise definition in the language of set theory as it's our style when talking about mathematics. Right? So let's draw out some of the elements of M and the natural numbers, and let's put some more pictures onto the diagram, eventually to lead to the idea of how we would define for two things to be essentially the same, two magmas to be essentially the same on this concrete example, but then we could generalize the idea maybe. So I'm going to make a drawing as I promised. So we'll have this empty word here that I'm not drawing because it's empty, and then there's further words made out of sticks. So that's my drawing on one side. On the other side, I'm going to list numbers 0, 1, 2, 3, 4, 5, and so on. And now these two magmas being essentially the same means that we have nice one-to-one correspondence between them, right? So empty word corresponds to 0, a single stick corresponds to number 1, 2 sticks correspond to 2, and so on. Let's call this correspondence some arbitrary name. Let's call this C, because it's correspondence. Now, this correspondence is not just a one-to-one correspondence between sets. There is a compatibility of the magma structures on the two sets. C of x dot y, right? What is x dot y? These are x and y are words in this magma of or monoid of sticks. And dot is the concatenation. So C of that, which counts how many sticks there are in the word, right? Equals C of x plus C of y. As we said here, if you take this word, you concatenate the two, and you count all together how many sticks you have in the word. That equals to the sum of number of sticks in one word and the number of sticks in the other. Now, this equality here is very similar to the other compatibility equality we had earlier, which was this one. How is it similar? You can think of this R just like that correspondence C. You see, you evaluate R at X, you evaluate R at Y, then you operate. That's what you do on one side of the equality. On the other side of the equality, you first operate, and then you evaluate with R. Just like here, where we evaluate C at X, evaluate C at Y, then operate, That's one side of the equality. It's the other side. Then we had the other one. So the signs have been switched around. And on the other side, we first operate and then we evaluate. So this idea of compatibility now starts to arise in two different settings. One in the story of viewing elements of a monoid as functions, and the other one in the story of trying to understand what does it mean that the monoid of sticks is essentially the same as the monoid of natural numbers. And in both cases, we seem to have some kind of a function C. In this case, it was called C. In the other case, it was called R. We could really kind of think of this R of X as R with subscript X as R of X, right? We can think of this entire thing as our function R, which assigns to X some value Rx. So this is a function R there with some compatibility law we wanted to require for a certain purpose. And then here we have a function C, which seems to be a function from this side to that side. But we could also consider it the other way around. But the way we wrote these things out here, we're considering it as a function from left to right. And again, some compatibility law that it must satisfy. So these two examples urge us to introduce the following definition. Given Magmas M and M prime, and let me call the operation of the M prime magma, let me call it dot prime. This is going to be a long word. A homomorphism F from one magma into another one is a function from M to M prime such that this compatibility law we spoke of holds. I apologize for this. I just want to make my screen a bit bigger. Such that f of x times y equals f of x times prime with f of y, such that this holds for all x and y elements of M. When F is a bijection, in addition to being a homomorphism, so we all know what a bijection is, right? So a one-to-one correspondence, just like in this picture, we have a one-to-one correspondence here. We say that F is an isomorphism. And this is the answer to our question, what does it mean that two magmas are essentially the same? It means...
Wait, Prof, you said when F is a bijection in addition to being a bijection.
Oh, thanks. I meant to say in addition to being a homomorphism. Thanks. So this answers our question of formalizing what it means for two magmas to be essentially the same, because that's exactly the scenario we have here. And this fully describes our feeling that this way of writing numbers and that way of writing numbers doesn't really change numbers. It's just a different way of writing them, right? And what amounts to there just being difference in writing is that we have a one-to-one correspondence such that operating with this notation is compatible with operating with the other notation, where the compatibility is the condition stated here. So in other words, we can now say in a bit more formal way what we mean when we say it's essentially the same as. We could say is isomorphic to. So the monoid of words in an alphabet having exactly one element is isomorphic to this specific monoid, where being isomorphic means that there exists an isomorphism. So let's put that in the definition as well. M dot is said to be isomorphic to M prime dot prime when an isomorphism from M dot to M prime dot prime exists. Now, the notion of isomorphism of structures, of mathematical structures in general, is one of the most fundamental notions, and indeed it serves the purpose of two structures being essentially the same. The way we have defined isomorphism here is a bit is not the most elegant way to define it. It is a correct definition, but there is a more elegant way of defining it, which would suggest to you how one would go about defining isomorphism of structures in general. But I have done this on purpose because historically this is how people approached it before they realized that there is a more general notion of isomorphism. And that more general, what makes the more general notion of isomorphism, that will conclude it as a property of this definition. Like the immediate question that comes to mind here is that if two magmas, if this magma is essentially the same as the other one, in other words, isomorphic to, if one thing is the same as the second one, then of course the second one should be the same as the first one, right? So is this reversible in the context of our definition? Is it true that if there is an isomorphism going from there to there, then will there be an isomorphism going from here to here? Well, this thing was a bijection, a one-to-one function, so we can always invert a one-to-one function, but it might not be so clear that when we invert the function, when we consider the inverse function, that inverse function is still obeys the compatibility law that will have to be proved, okay? And in fact, that will be our next theorem.
Wait. So, Prof, in this case, would the homomorphism be addition and concatenation? That they're essentially a similar operation.
Yeah. So in this case, we have a homomorphism, which is actually an isomorphism from the monoid of sticks, where operation is concatenation, to the monoid of natural numbers, where operation is addition. And that homomorphism is described here. So to a stick, to a word of sticks, you map that to the number of sticks in the word. That's the number that you map it to. That's the value of your function at the word. For any isomorphism from one magma to another one, the inverse function, and I'm assuming that you understand that if I have a bijection, if I have a one-to-one function, then it will have an inverse function. If that's something new to you, we could go into discussing that maybe after the session. For any homomorphism f between magmas, the inverse function f minus 1 going from m prime back to m it isn't, sorry, I think I said homomorphism, I meant isomorphism. Is an isomorphism going backwards. From the m prime magma to the m magma. Well, the thing is that f minus 1 is clearly a bijection, because f is a one-to-one function, its inverse will also be a one-to-one function. But now we want to prove that it preserves its compatibility law, right? So we want to prove that, so required to prove is that f minus 1 of x, let me actually call it a dot prime b equals f minus 1 of a dot f minus 1 of b. That's what we want to prove, right? So we are going to prove that by a series of computations, I mean. So let's consider this expression, and keeping in mind that f was a one-to-one function, in other words, bijection, every a, right? Every a can be written out as f of f inverse of a, right? So I could write this as f of f inverse of a. So that's the whole idea of the function f and its inverse. So when you apply the inverse function and then you apply f function, you get back the same element. In this case, the same element a. So a equals that, and on the other hand, b also equals to something similar, right? And now we have this, which is completely wrong, or is it not wrong? No, it is not wrong. Sorry, it's completely right. And we now have a situation where we are using f and applying it to some element, and then multiplying that with f applied to another element. But remember that f is compatible. F has this compatibility law, right? So f makes the two operations compatible. So I could actually rewrite this as f of whatever is inside here multiplied with whatever is inside there. So that will be f of f inverse a multiplied with f inverse b. There we go. But now, what do I have here? I have this thing to which f is applied, and then f inverse is applied. But f and f inverse, they cancel each other out, right? So then I could just write this to be the inside part, which gives me f inverse a dot f inverse b. And that's exactly what I wanted to prove, isn't it? See, this is one side, and that's the other side. Okay. Now, there are many other facts about isomorphism we could establish apart from this one. For instance, here's an example. If f from m dot to m prime dot prime, and on, so we have f from one magma to another, and also another function g from that other magma to a third magma. So if both of these, if they are isomorphisms, well, actually, let me just restrict to homomorphisms. The results about isomorphisms I had in mind can then be derived from this result. If f and g are homomorphisms, then their composite function, when we apply one function and then we apply the other one, then G composed with F is going to be a homomorphism from M dot to M double prime dot double prime. And I want to leave the proof of this as an exercise. Now, the reason why I wanted to state this, because in the case when F actually is an isomorphism, right, then this composite will be an isomorphism. And so we can say that, why will it be an isomorphism? Because composite of bijections is a bijection. And now we know it's also homomorphism by this theorem. And so we can say that if one magma is essentially the same as another, and that other is essentially the same as some third magma, then we know that the first one ought to be essentially the same as the third one. So this idea of two structures being kind of same, which when there is an isomorphism between them, that idea really kind of obeys the principles of being same. Like if A is the same as B and B is the same as C, then definitely A must be the same as C, right? And these kinds of facts hold true here. Any questions? Okay, if there are no questions, then I would like to summarize what we discussed today.
Can I ask a question?
Yes, please.
So actually, does like the last theorem kind of like display a transitive relation,
Yes,
something like that?
yes. It
Okay.
states transitivity of the relation of being isomorphic.
Oh, okay. Thank you.
Well done. Yeah. Okay, so let's summarize what we did in this session. Let's go all the way back. So this course is a course on mathematical structures, and we began listing of what they could be. We had one very primitive example where a mathematical structure is just a set, and then another one, a bit more elaborate one, where it was a set together with a binary operation. We called such a thing a magma. And then we continued on and started working with magmas and proving theorems about them and introducing some concepts in the context of magmas. So the first thing was the formal definition of a magma as an ordered pair. Now, in set theory, an ordered pair can be formalized purely in the language of sets. So, ordered pair of two components, A and B, can be defined as the set of two elements. The first one is the set of just A, and the second one is the set of A and B. So, this is why, by defining a magma as an ordered pair, we're actually defining magma as a certain kind of a set, namely this kind of a set where A is M and B is the function seen also as a set. Every function can be seen as a set, namely the set of ordered pairs of X and the corresponding Y value. Then we look at some examples of this structure. After that, we introduced the notion of an identity element, which is a particularly well-behaved element in terms that it kind of respects all the other elements. If you multiply with something else, you get back that other thing. And we looked at what identity elements could there be in the examples we had. And we saw that in some cases, identity elements might not exist. And then we proved a general theorem that when identity element does exist, that's the theorem, then it must be exactly one such. And after that, we started looking at magmas in a bit of kind of geometric perspective, where we want to really think of each element of a magma as a function defined on the set. And this geometric perspective led us to formulating a theorem that said that the familiar associativity law for a binary operation captures the idea that, in the terminology we introduced later, that this function, the representation function, that's why I call this R, that represents every element as a function, that representation function is actually a homomorphism. So this is the rule that says that the R function is a homomorphism. So for the representation function to be homomorphism is equivalent for the starting magma to be associative, and that's what this theorem states. In a bit more conceptual terms introduced later. Okay, so, well, we had this one example of the representation of thinking of every number as shifting the number line by that number, so by adding n. And then once we saw that this notion of associativity emerges kind of naturally in the context of this geometric interpretation of magmas, we wanted to give a name to a magma where the operation is associative. We call it a semigroup. And a semigroup together with identity element is called a monoid. So it's combining the two ideas of associativity and identity element. And then we looked at a completely different example of a monoid than what we might have anticipated before, based on a suggestion, or rather on a remark about relation between associativity and commutativity. And so this monoid of words that we looked at, it turns out to be an example of a monoid where you do have associativity, otherwise it wouldn't be a monoid, right? But commutativity fails. In fact, we were able to characterize when is the monoid of words commutative. It turned out to be only in the case when either our alphabet is empty or it has exactly one element. Now, investigating this peculiar special case when the alphabet has exactly one element has made us realize that in that special case, our words look very much like natural numbers, right? And then we wanted to formalize that idea of what does it mean for this magma to look similar to that magma. The similarity is displayed by a mapping with another compatibility rule, which is very similar to the previous one. So that led us to this notion of a homomorphism between magmas. We defined what a homomorphism was. We finally were able to fit our intuitive idea of compatibility of operations into a formal definition that constitutes a homomorphism. And then we were able to define this to make precise the idea of two magmas being essentially the same by saying that means that we must have a homomorphism, which on top of being a homomorphism is a bijection, and we call such a thing an isomorphism. And then we proved we just played around with the notion of isomorphism. We proved various interesting things about isomorphisms. For example, when there is an isomorphism F, there is always something going backwards. And in relation to your remark, Ponza, if our last theorem was transitivity of the isomorphic relation, this of course is symmetry, right? So having something going backwards allows us to say that if this is isomorphic to that, then backwards this will be isomorphic to that as well. So we looked at symmetry of this relation of two structures being isomorphic, specifically two magmas being isomorphic. And then we also looked at transitivity, which was actually a consequence of a more general theorem saying that when you have two homomorphisms, F and G, and you compose them, the result will still be a homomorphism. But we didn't prove this theorem. The proof of this theorem was left as an exercise. Now, the development of the theory of magmas that we gave here, well, of course, this is just like the very beginning, right? But interestingly, the kind of topics we touched on here will be reoccurring in various different other contexts of other mathematical structures. All of these ideas, the idea of homomorphism, the idea of isomorphism, the idea of defining certain types of elements in my structure, like the identity element, for example, these ideas will be recurring ideas. When we will be considering other mathematical structures, we would want to also define homomorphisms between those, or isomorphism between such structures, and so on. So, on one hand, we learned a bit about Magmas, but on the other hand, we got exposed to some material which will reoccur several different times when we'll be looking at other mathematical structures. Now, in my final couple of minutes, I want to touch on the question that might be arising in your minds. What is the use of Magmas? How do they apply? Where do we need them? And the answer to that question is that every time you have a binary operation that you work with, it could be addition of vectors, right? It could be multiplication of numbers and so on. All of these times you have a magma there. And so magmas are everywhere. We just never gave that structure a name, otherwise we've been using it all the time. Moreover, the notion of isomorphism between magmas is something also that has featured lots of times without us maybe explicitly seeing that. So I want to conclude with one example of an isomorphism of magmas, which is something that is very familiar to everyone. So let's consider two magmas. One will be the magma of real numbers, with operation being multiplication of real numbers. The other magma will be the magma of positive real numbers, so real numbers that are strictly bigger than 0. And the operation there, okay, my apologies, I actually wanted the other way around. So I want this one to be considered with addition, and the other one I want to be considered with multiplication. The function f between these two magmas will be defined as follows: f of x equals e to the power x. We all know what that is, right? Now let's write down what it means for this f to be a homomorphism. Well, homomorphism property is that f of x, I'm writing plus y because keeping in mind that I have plus operation in my source of my function, right? That needs to equal to f of x times f of y. Poncho, there will be no second session today. We will finish just now, and the other session will be just for a general discussion. It will not be recorded either. But thanks for your message. So this is the rule of f being a homomorphism. And if we spell this rule out in terms of this specific function, we get what? E to the power x plus y equals e to the power x times e to the power y. On top of that, we know that this function is a bijection, right? It's a bijection. How do we know that? Well, we can already tell it from the graph, right? This function e to the x is a bijection from the set of real numbers to the set of positive real numbers. So we get that this f of x, which is e to the x, is an isomorphism of magmas from the magma of additive real numbers to the magma of multiplicative positive real numbers. Let me just leave it like that. Okay, so that was the last example. To conclude the session, if you have any questions, please ask. Otherwise, we will stop the recording, and then we can, after the recording, have further discussion.
So Is the identity element only unique for the magmas, or it's like in general it's unique?
Well, magmas are very general, right? We didn't put any restrictions on the operation. So identity element will always be unique because magmas are as general as you can get.
Oh, okay, thank you.
Any other questions?
I was thinking about this earlier. Is there any sort of theorem, or has it been shown or shown not the case, that you can take any composition of magmas and simplify it down to a single magma?
What do you mean by composition of two magmas?
Sorry, I didn't hear your question, or didn't hear your answer for a second. Something bugged with my.
What do you mean by composition of two magmas?
So it was around the part where we were taking we were talking about associativity with like xy and a third element z.
Right.
But,
It was not composition of magmas. It was composition of functions, right?
Well, or composition of functions. But okay, so maybe then I need to rephrase my question. But I suppose maybe my question would have more been, can you always make recompartmentalize it into a single operation of two elements in the case of the operations being magmas?
Chad, I think you need to think further about your question because, to be honest, I think what you're saying.
For example, I'll write down my question I'll think about my question more, possibly write it down better, and then ask you another time maybe.
Sure. Okay. Yeah. We can also discuss it after the session. I mean, after the lecture. So okay. So anyone else has any other question? All right. So if there are no other questions, I'm going to stop this recording.